Right. I'm hoping this little video might help you a little bit with trying to envision or come to grips with molecular polarity. I mean, we've been talking in class about how you determine whether a molecule is polar or not. We look at bond polarity first, and then we look at the arrangement of bonds. So we can talk about something like carbon dioxide, CO2. So we do know that the carbon-oxygen bond here is a polar bond. The delta N is quite large. Oxygen having a higher electron negativity. So that's a polar bond. And so this is also a polar bond. So we have two polar bonds. Now we look at the arrangement of those polar bonds, and you'll remember there's two electron domains. Steric number's 2. They're both bonding domains, so it's AX2, and so that makes it linear. And so a linear molecule, the name says it all, the arrangement of the bonds means those bond dipoles, these two polar bonds, cancel each other out. And I talk about the flip test, and basically I say you should be able to grab one of the bonded atoms and cover the other one, and you want to flip this, and if you get the same thing on the other side, then you have non-polarity. So if we flip it, we get the same thing. So that's what I mean by the flip test. Flip test kind of becomes a little more difficult when we have something like this, and so this is carbon tetrafluoride or tetrafluoromethane, depending on what you want to call it. But again, these are definitely polar bonds. Carbon-fluorine bonds are all polar. If we do the flip test, so I want to do the flip test with this particular bond here, I'm going to see if it gets canceled out. So I grab it and I flip it, and it doesn't look so simple. It's not so easy to see how that flip test works. And I have been mentioning about vector analysis, so let's talk a little bit about vector analysis right now. Okay, so what I want to try to get across today, I've been talking a little bit about bond polarities and bond dipoles, and these dipoles canceling each other out. And I keep mentioning that there's a mathematical component to this. And so I do just want to show you that this is mathematical. So we apply it in chemistry, but the math supports that chemistry. The math proves that it does actually, in fact, cancel out. And so you can see something on your screen here, and I have no idea what this means. So I've got a friend who's going to give us a hand. And so Mr. Holman's going to take us through the math side of things, and then we'll take it from there after we're done with the math.
Okay, hi. So what we have is we have three vectors starting at the same origin point. They're equal vectors, and a vector is something that's got both magnitude and direction. So what we've got is an angle of 120 degrees between each of the vectors. So what we want to do is we want to show that when you add the vectors or add the forces, we end up with a net force of 0. So what I'm going to do is I'm going to take this vector, and whoops, wrong one. I'm going to take this and move it to the end of that vector. So what I've done is I've taken the start of my second vector, put it at the end of my first vector, and I take my third vector and I move it. And if you notice, when you put them all together, all the forces balance out, or you end back where you started. So there's a net result of 0. So I'm just going to move them back. That's the basis behind what we're going to talk about in a moment. So we're going to move on to the next slide. So what I've done here is we've oriented three vectors. Now what I did was I might as well make one go up and down because it gives me a little, or saves me a little bit of work. So what I'm going to do is I'm going to take my vectors, and what I'm going to do is I'm going to break them up into horizontal components, which is this part, and vertical components, which is that part. If you've taken physics, you've already done this already probably. So what I'm doing is I'm going to take this vector here, figure out the x part of it and the y part of it, and when you add them together, you get their original vector. Similarly, I'm going to have a vector going this way and up. When you add them together, you get this one. And I've still got this vector, which is all f of y. It's only going up and down, so I don't need to break that one up. It saves me a little bit of work. Okay, so we're going to move on. Now what I've done is, since all my angles were 120 degrees, we've got a 90-degree angle here. That leaves us with 30 degrees here. So using a little bit of trigonometry, the sine of 30 is the magnitude of my y force divided by the magnitude of the original force. And then if we use our little right angle triangle over here, sine of 30 is a half, right? Opposite over hypotenuse. So I put the 1/2 in here, and what we figure out is the y force here is half the magnitude of our original force. Similarly, repeat the same thing on the other side, and this y force is half the original magnitude force as well. And then what I can do is I can take this force, I'm just going to set it really close just so you can see them side by side, set it there, take this force, move it over here, and you'll notice I've got two forces up and one force down that balance it out. So right now in this diagram here, the net y force, or up and down force, is 0. So the the y parts balance out. Now I'm going to go on to the next part. And similarly, if I took the cosine of 30, which is adjacent over hypotenuse, so root 3 over 2, root 3 over 2 is the magnitude of the force of x divided by the magnitude of the original force, so that works out to be root 3 over 2. For the purpose of this, the actual math doesn't really matter, but we have a force going in the right direction of root 3 over 2, and we have the exact same magnitude force heading in the left direction, hence the little negative here, which is negative root 3 over 2. Or, more basically, this force and this force have the same magnitude but opposite directions. So when I add those, I've got a force going that way, and I've got a force going this way, and you'll notice they're the exact same magnitude, so there's no net movement in horizontally. So when we go back, when we combine all of this, this one showed we had no up and down force, this one shows we have no horizontal force. So if there's no up-down force, no horizontal force, these forces all balance out, which is called an equilibrium, or there's a net movement of 0.
So can I just ask you, Mr. Holman, so what you've shown is if for example, I put an atom on the end here, I'm just going to make that an atom. So I have that atom, and I put atoms all over the place. And those are all the same atoms with the same electronegativity. That might be a term you don't remember, but what I have is a force from the central atom here towards this atom on the right. I have a force from the central atom to this atom on the left, and I have a force from the central atom to this atom down below. All those forces are identical, so what you've just shown us is that the net sum of all those forces is going to be 0 because there's no movement or displacement of that force, or however that's termed. Is that right?
That would be exactly correct. As long as the forces are exactly the same, all these angles would have to be the same, and then based on that, all the net forces would turn out to be 0. As long as all those angles are the same, which they have to be, yeah. If I remember my grade 12, or actually in my date, grade 13 chemistry, that's the way it works. So it's a little bit of math being applied here.
That's perfect. So anything with the same bond angles would have no molecular polarity. That's basically what Mr. Holmes just tried to show us.
Right, now we've shown it two-dimensionally. So what I've got here is just a quick little view of what happens if we work in 3 dimensions, which is a little hard to see. But if we were to go with 4 bonds, all the angles would turn out to be 109 degrees. So if we looked at this one as our first starting point, if you work 109 degrees off this axis, 109 degrees off this axis, and 109 degrees off this axis, we would come up with the next force. And if we did that 2 more times, we would have all 4 forces showing. And it's a little hard to see, but what we would end up with is a vector that's going to be coming forward, left, and up. And the important part is this vector and this vector could always be broken down, and the other two obviously could be broken down into x parts, y parts, and z parts. Unlike the previous part, which was 2 dimensions, we only had x parts and y parts. But when we break it into 3 dimensions, you'll have all 3 parts. And then when you summed up all the x's, the result would be 0. When you summed up all the y forces, the result would be 0. And when you sum up all the z's, the result would be 0.
So again, if you had 4 bonded atoms, you're going to have x, y, z orientations for those atoms from the central atom. And again, as long as all the atoms are the same, the net force, net displacement is going to be 0. And so the molecule has no net charge, no sum of charges.
Right, and you could add as many atoms as you wanted, or bonds, I guess. The same thing is as you add more, the angles would change, but the angles would still be the same because of the magnitudes of the
balance of the forces of repulsion.
Yeah.
That's right.
That's
okay.
Not a math term there, kids. But anyway, but all those angles would still be the same, and you take any of those forces, and they would still have x, y, and z components, and all the x, y, and z components would always add up.
All right. Well, that's great. So I think that covers the math side of things now. That's not going to be in your test.
That's the most important part, though, the math side, kids.
But what we have tried to show you here is that you get a polar molecule when you have unequal forces. If the forces are the same, even though the bonds are polar, the molecule will not be polar. And again, the geometry, the vector analysis that Mr. Holman's just showed us is what shows us the molecule ends up being nonpolar. So we're done for now.
Been a pleasure helping you guys out with a little bit of math, and perhaps we'll do it again sometime. And also, for those people taking calculus, this will come up in the third term.
All right, well, that was really good of Mr. Holman to take us through some of that math, albeit a little scary, I must say, some of that stuff. It's been a long time since I've had to worry about that. But what I think it is useful in knowing is that when I talk about bonds canceling out, they really do cancel out. There is a mathematical demonstration of that, and that's what Mr. Holman is trying to get across. We can look at a trigonal planar molecule now. I think maybe have a bit better understanding about why, if I have three polar bonds, the molecule, because of the arrangement of those bonds, is nonpolar because the vectors, the forces that are a component of a polar bond, cancel out because of the arrangement of the bonds. So it's not too hard to see with the trigonal planar, perhaps a little harder to see with that tetrahedron. But again, Mr. Holman did show that you have x, y, and z directions for those forces because all the bond angles are the same, and he did mention that the bond angles have to be the same, but because they are, and because the forces are all identical, the x, y, and z vectors will cancel out. And if the vectors cancel out, a molecule with four polar bonds arranged in this fashion will actually be nonpolar. Now, you can actually change that. You can make it polar with the same geometry by doing this. And so, again, I would hope you'd realize now I've changed things. It's still tetrahedral geometry, but I have a different force. And as soon as I have a different force, I lose the cancellation of all those forces because one of them is different. And so this molecule, even though it's tetrahedral, would now be a polar molecule because one of the bond dipoles is different. Anyway, I hope that helps or it helps you come to terms a little bit with how we look at molecular polarity and how the geometry affects it and the direction of these forces. So that's it for this video.